So in the style of the whole day, without a lot of introduction, I'm just going to hand the floor over to Addison, that is here to moderate our panel. And, Addison, take it away.
Thanks, Jan. Hi, everybody. I'm Addison Snell with Intersect 360 Research. We're analysts who cover the high-performance computing and hyperscale markets, including topics like cloud, big data, and AI, to the extent that they overlap into this space. We've heard a lot of really great presentations today, focusing in particular on the topics of Exascale and carrying that forward. Fortunately, all of our panelists have already presented, because I don't really like panels that are just a sequence of presentations. I prefer moderate a panel that's in the format of a panel. This way we get to ask questions to our panelists. Some of them brought up a few provocative statements. I'd like to get that conversation started between them, and hopefully have time for some audience questions as well. Now, on the topic of industry readiness for Exascale, I think one of the most interesting questions is to try to take it from the theoretical to the practical and ask, what do you foresee are some of the first specific commercial applications that you think will actually take advantage of Exascale? And Mike, I'll start with you because you sat on my left.
I can give a flippant answer. For some definitions of Exascale, it will be Google search.
Let's call that a hyperscale application for right now, as opposed to an Exascale application.
Yeah.
All right, for the purpose of this panel, let's go ahead and acknowledge there's the whole hyperscale industry, Google, Facebook, and Apple and all those. Let's take those out of the equation because they focus a little more on scale than on performance. We're talking about scientific HPC applications running at scale. If you want to include AI in that, if it's going to be an AI application that's actually running at Exascale, go ahead. But take those out and take another shot now that I give you a chance to catch your breath and think.
Okay, if you want to include AI applications running on 16-bit floating point operations, they are certainly going to really make big use of the accelerators that are doing the reduced precision matrix multiply. So that's going to be a very interesting thing, pushing the Exascale bounds real quickly. But these are not double precision flops. Do
you think there are any double precision traditional HPC applications that'll get there? Or what do you think will be the first one? Or do you want me to go down the row and then come back to you?
Yes.
All right.
Next.
Who wants to go first? Rather than me picking on somebody.
A clarification question.
Sure.
You're talking specifically about stuff that's in premise, or are you trying to cover systems that are anywhere but in the cloud? Or
may I help you, my friend?
I'm not sure what you mean. Covering by
what specific scientific applications, commercial ones, do you think will be first running at Exascale?
But not in the cloud. Anywhere.
Anywhere,
okay.
But I'm separating out hyperscale from HPC. Okay. Google search isn't really an HPC application, it's a hyperscale application.
But you gotta understand, that's where the money is. And so whatever he develops, if he's not doing it for Google, he's not gonna do it at all.
Let me rephrase my question.
You're gonna get the same answer.
Do we think that Exascale can benefit commercial HPC applications, yes or no?
Yes.
Great. Pick an application. What do you think will get there?
I think I just finished talking about some of them.
Yeah.
No, so, it would not surprise me if the petroleum industry is able to buy that level of compute. Similar, as long as the cost is similar to what we have today.
All right, so let's drill into that. You've got the petroleum industry. What are the specific applications that you're looking at that you say this is what can really go to Exascale?
Seismic imaging applications.
Seismic imaging applications because of what you were just talking about. Outside oil and gas, do we have any?
So even in seismic, I mean, does anybody here actually think they can strong scale some of those things all the way to Exascale? I mean, this is
we don't want necessarily strong scale.
Okay.
The problems we're talking about are just making a bigger problem. increasing the frequency, increasing the complexity of the medium, many more iterations to solve a problem more accurately.
Let me ask you a question. Go ahead, Odd.
So multiple copies, I think, in parallel, sure, anybody can load an Exascale system, right? And everybody would love it. But I don't know, actually, and your question is asking for a true commercial application that can actually run in an Exascale system.
Somewhere between it's hopeless and no one can do it versus, yeah, in general, everyone can do it.
So,
there ought to be specific applications that do it first.
So it's the whole difference between, the whole definition of capability versus capacity, right? I don't know, and honestly, I don't know. If there is something in the commercial world, true commercial HPC, that can really scale on one load, one run, all the way to an Exascale system, or that's any close to that today. And maybe someone in the audience has an idea, but
Hey, so Scott, quick question. Sure. What are your pain points today? I mean, if you had infinite compute or you had infinite, what are your pain points? What's keeping you from doing your job?
There's significant effort in doing a better job of some of these problems, of solving these problems in an algorithmic sense. It's the algorithm, the geophysical or mathematical algorithm, I would say. There's some things that you could do just increasing your frequency, and that would increase your cost by, you double it, it's a factor of 16. But you may or may not get value from just that. But certainly some of those things that we were talking about are algorithmic changes that would require research efforts to bring to fruition.
This is making me a little bit sad here. I thought it was starting with kind of a softball, especially considering I sent you guys these questions last week. Let me turn it around. Let me turn it around this way. So I'll start. Let's go out of oil and gas, and let's say finance, for example. The risk management applications they have now are actually, the best of breed of them could use something like a Petascale system to resolve all of their risk portfolios overnight. That's best of breed. But go beyond that, they would like to do intraday checks on their risk portfolio. Otherwise, you've got a portfolio manager who you know where he is at 8 a.m., and all day long he can go wherever he wants as long as he comes home by 4, and then you don't know if that's where you want him anymore. Going to intraday checks, or ideally something close to real-time rebalancing of risk portfolio, to real-time rebalancing of risk in response to change in real time, in response to changing market conditions, that's an exascale application. Do I think they're going to get there in 2021? No. I do think they'll get there in the next decade. I think oil and gas probably gets there first. So I think there are industrial HPC applications that get to exascale. Let's flip around the other side of this, is what are the gaps that keep that from happening before it becomes practical?
Well,
go ahead, Thor.
Potentially, and what do we think of the idea of precision medicine, right, and cancer diagnosis, and the ability to really map somebody's drug prescriptions to their particular cancer that they're dealing with, and the ability to do scan automatically millions of records of other cancer
I'm only an
patients that are out
industry
there.
analyst. What do you think of precision medicine?
I mean, certainly that is one that we all emotionally and perhaps personally feel we'd love to see that push the outer bounds of the compute capability, because there you have millions of records that you want to be able to do pattern detection or correlation. As well as the ability to prescribe and not guess, right, the kinds of drugs that people would benefit from in their situation.
You asked me what I thought of it. I think when we go to AI, things like precision medicine, every new technology advancement we've ever heard of is always going to revolutionize medicine. It's the first one we go to. It's very marketable. I believe precision medicine is coming, but it's kind of the high buzzy marketing one. I think you're going to have a personalized interest rate with AI way before you have personalized drugs with AI. I guess, again, there's more money in finance. I think that drives a lot of the innovation there. But now you're getting on the right track, at least, to specific applications.
Well, I learned one hard lesson in doing this, and that is, if you want to know who is most likely to succeed first at Exascale, you have to look at who's really running efficiently on a 20 petaflop machine. Even though the architectures will change a lot, it's very hard to go from, half a petaflop to an exaflop. I mean, you have to look at who's really ridden the sort of crest of HPC and who really understands their algorithms and who has been doing this for 10 years, 15 years. So this industry would be a very good candidate. I mean, people who have 10 petaflop machines already and have really struggled with that. I've seen very few, if any, cases of jumping, a couple of orders of magnitude computing performance. So,
and to your point there are very few industries that are running at petascale today.
Issue.
Oil and gas is the notable one. I did sit up and take notice of the chemical engineering system now going into petascale. That's been on our watch list for applications for a while as they migrate from just the process side, like CFD of a mixed tank, into actual discovery side, like we've seen in the pharmaceutical area. Moving that into chemical engineering makes a lot of sense.
But before you transition, I think, so it's how, and we got the question, but I guess I wanted to let you ask it like that because I knew how it would turn. I think Tor...
You were waiting for everyone to get riled up. I like it, Nick, thanks.
Tor basically put it, so it's not so much about what commercial application exists today that will scale to Exascale. I mean, they will scale, there will be more copies, there will be more capable. So that's all good, and I think everybody understands that. It's about what a system like that will enable as new grand science problem that will then transfer into commercial applications. So predictive medicine is one. Think about the human brain project, right? Being able to model full human brain and what these guys are doing on that, and then apply that to, there's all hopes of Alzheimer's, understanding Alzheimer's, Parkinson's, and that has huge impact on the commercial aspect of it. Then think about, one of the other grand challenges, full-scale climate projection, right? So then you can say, oh, that's not commercial, and maybe that's not a very popular topic in an oil and gas conference, or maybe it is actually. but this has huge commercial impact eventually because, and this is the kind of problem you just can't handle at the right resolution today. So it's not so much about what we do today that we want to scale up, is about what we can't do today that will have huge commercial impact in the next decade, I think so. That's why I wanted you to ask the question so I could steer it.
I love that you brought up the brain project because that's one. If we all were trying to remember way back to the year 2000, it's hard. But we mapped the genome, and that's when you say we did that, scientific achievement is like this. It sounds like the end of a problem. It's done. We mapped it. The truth is, it's the start of the whole new field of genomics, right? And I think we're getting close to that with brain research. We might be within a decade now of the first time on a supercomputer we get a comprehensive map of a human brain, which sounds like, okay, it's done, but it will set us off embarking on a whole new field of brain research, not all of which will be commercial exascale at the time, but it will be an entire new field of research. So what do we think of all of the diversity of processor architectures that are out there? We've heard a lot about different approaches. How should end users out there be evaluating all of these? Like, okay, I'm going to go all in on GPUs or FPGAs or Xeon Phi, and I'm worried that in 5 years maybe I made the right choice, the wrong choice. How do I know? We've got a diversity of how the national labs are approaching, and how should end users evaluate it?
Ask the processor guys first.
Well, so one of the things that I referenced earlier this afternoon was just the convergence of simulation and modeling and AI and big data. And certainly, if you have scalability of an architecture that can support many workloads, then you have certainly a faster path towards addressing some of these challenges. One of the things I didn't mention, for example, is software-defined visualization, right? The ability to run through open source codes all of the rendering, rasterization that you need for something like a supercomputer. So the idea that says I can run a variety of workloads on my existing infrastructure, or as I build it out, add more capability. That kind of flexibility is certainly what we'd like to see. To your point, if you go down a certain path, you pick the wrong one, there's a challenge or a cost to that.
Mike, you were trying to jump in there.
Yeah, just to boost Nick's previous point, back one question. There is an observation that when you improve the cost performance of compute by an order of magnitude, people start doing new things with it that no one ever expected before. So that could be something that plays out here. In terms of the specific question on hardware architecture, this is almost a business question. It's not just what is the processor architecture, it's the software support, it's what's the memory system available on that, a lot of other functions and features. And it's very hard to answer in the abstract like that because it's such a business-related question. I will add that for some applications, it's the memory system you can buy, which may dominate the whole question of which system you want to go with.
Unfortunately, I just broke this chair, so I'm going to have to come over here. It's probably not the last time that's going to happen either.
Here, I'm the moderator. I can stand.
Okay. No, I'm fine. I think Mike hit on a really big thing. In all the years and the people that I've talked to, and Thor said this too, it's the ecosystem that's available for people to develop on that has really driven a lot of their choices. I remember years ago when NVIDIA was just coming out with the GPU, and everybody said it was going to change the landscape. It's taken the software almost a decade to get it to the point where people really see it as something that's a viable architecture for more than just visualization. I mean, you guys kind of pioneered it, but I remember having a conversation with JP Morgan Chase, and they said, hey, we're going to look at it, but if there's not a 10x performance improvement, we don't care, because I'm not going to take my production coders offline to go do this if I'm not going to see a significant benefit. So it really depends on the ecosystem that's available, and that's the advantage that the x86 architecture's had for years, is because they've had a development community over 40 years to develop code for it that's really kind of hard to unseat it. But the GPU and NVIDIA's investment has done really well there.
So I'd say the application perspective, there's a huge software problem, and people are going to use their current programming model as long as they possibly can get away with it. Okay, and around now, when you look at the leading edge of HPC, is probably one that's starting to get away from them. Okay, where we have a large cluster, for example, that you can program pretty straightforward way with MPI and OpenMP, say. They're going to hold on to that as long as until they're convinced that they can't get what they want out of that. So what I imagine what will happen is that those programming models might become available or might remain available, but they might not get you the performance. It will be a bit of, you'll be able to compile easily, you'll feel good about it, you'll be able to run your code, but you'll get further and further away from the achievable performance of the machine. And at some point, they'll have to invest in software. And then you have to look at a small group of guinea pigs who were out on the leading edge and who were willing to try these things out years ahead of time, I think. And so that's one of the roles of the ECP project, and I'm sure others as well in DOE, is to just have some people who are going to take the risk, who are going to work with the vendors, and who are going to be willing to do crazy things, and then inform people a year or two behind about what they can ignore and what actually worked. There's a huge software problem because the investments are tremendous in validation and just building up the code base. There's a mission to the applications. There's a huge risk associated with doing something crazy. And that's true even in the research space, not just the commercial space, for people's research careers or whatever.
I agree with that point, and that's something we've observed in the market. In fact, I wrote a blog about that 10 years ago as we were moving into the multi-core era. This is what you were talking about with the end of Dennard scaling, which is really what forced this problem onto people. And I had the image of Wile E. Coyote has run off the cliff, but he doesn't fall yet because he hasn't looked down yet, right? And there's this cartoon physics, and the compensation in the industry has been to add more and more main memory into the computer. The amount of memory per core has remained nearly constant in configurations. It's actually gone up slightly over the last 10 years, which means the amount of memory per socket per node has gone up exponentially in these systems, where memory becomes ever more important. Yes?
but not the bandwidth. And that's your biggest problem.
Correct, I know, but
so-
people are trying to compensate by adding in more memory.
So, yeah, but that doesn't work. So so I'll answer your question very differently. So sorry for the processor guys. I think the ISA doesn't matter. So when I was on a panel at the Exascale Compute Conference last year, there was an application scientist, I think from Sandia, that asked, so how many nodes am I going to have on an Exascale system? And that was a spot-on question. Why does that matter to him? Because he wants to know how he's going to domain decompose his whole application and how he's going to have to scale it out. And then, Al Gara was there, and anyway, so Al goes and gives a flops explanation, and I go like, well, I don't think the flops matter. So assume you're going to have, like, I picked a number, like 64 gigabytes of HBM in that time frame. Take your whole domain, right, and divide it by 64 gigabytes, and that's how many nodes you're going to need to basically scale across that system. Because co-packaged memory gives you 10x the bandwidth over what you get today. That's what you want to target for. Once you get that, the flops will follow, basically. So that's so I make a big argument for Steve there.
You did. You gave a whole argument about flops not mattering while you had your back to Thor.
I know.
Which was really impressive.
We're all about
Thor, what do you think?
I mean, it's all about balanced computing for sure. And Steve in his talk articulated the bytes per flop, and those are realities, right? So it's not it's about feeding the flops, and certainly the ideas of high bandwidth memory or persistent memory. Memory hierarchy, those are critical things so it's not just about cores and frequencies.
So the next question is for Scott. And sorry, I don't want to
Go ahead.
Moderating this panel. Go ahead. I want to hear this, actually.
So the next question is for Scott. Would Scott rather get an exaflop or would rather get 10 petabytes, which is like 2 orders of magnitude less, but 10 petabytes of very fast HBM?
And do you have a purchase order with you now?
I'm not sure of the answer. I mean, it depends on the benchmarks. We'd do that and see which gives us better overall throughput.
Well, I mean, Mike and Steve, where do you stand on this flops don't matter, it matters how you keep the flops fed?
Well, I work for a processor company, but I'm in charge of the memory strategy for it.
That's true.
So I sympathize that. It's an old joke. You build a machine by the number of memory controllers you want to put in there, and then you make sure you have enough floating point units to feed those memory controllers, because floating point units are really cheap nowadays. So figure out how many you need, throw in an extra 20% just to be sure, and then you're set.
Steve?
I'm not sure I'd say flops don't matter. I would certainly say instruction set doesn't matter. But I think at some point in time, Thor's right. If you've got balance, so let's assume that we spent the last 20 years just providing just gobs of memory bandwidth and not enough floating point performance, we'd be sitting here today saying we need more flops, we need more flops, we need more flops.
We're talking about the compute side of the house. How does storage need to evolve at Exascale? Anyone have an opinion? And consider the whole range of storage technologies, right? We've got non-volatile memory coming in is really blurring the line between what's memory and what's storage. We can get to where we're starting to think of memory as a tier of the storage architecture.
Well, but then again, boy, I hate to keep harping on this, but thank you for doing this. It really depends on the software. I mean, the biggest issue that happens right now, the hardware guys did a great job on nanosecond latencies of adding threading, hardware threading, and be able to do context switching while you're waiting for data to come back to memory. Going out to a large storage array, where it takes milliseconds or seconds to get that data, taking a 10, 15 millisecond context switch is really no big deal. Now you got the problem of if you have an SSD and you put it in your platform and you can have 50 microseconds of latency, now all of a sudden an OS context switch is a really big problem. And we've got to be able to have the point where the application now can manage its memory. And I think you guys do that already, but using, having capabilities like remote DMA and whatnot, so you allow the application to be able to deal with that very fast NAND memory, because we are going to get to the point where we've got sub 10 microseconds of latency across at least a couple of racks. And the software is going to have to be able to handle that. Otherwise, it really isn't going to matter or have a benefit.
He's looking at you, Mike.
I agree that this storage area is becoming really interesting. There used to be a claim that flash had just about reached the end of its life and scaling. Then we went to this 3D flash scheme, which just opened up the floodgates. Steve can't say this, but I will. We're going to have 1 terabit flash chips before too long. And that's just going to be just changing the way we look at storage from this point on. They're going to be a little bit flaky. There's going to be big ECC codes on them and so on, but they're going to be very usable.
We're talking about flash a lot here, but we're also talking about the prefix exa. And I'm having a hard time thinking about these exabyte and multi-exabyte all-flash arrays. Is that really where we're going, or are we looking at disk? Are we looking at tape? Are we looking, what's the tiered storage strategy here?
So it's definitely cheaper than spin torque or phase change, but the flash, I mean. So I had that on my slide, and that slide was done before you sent that question. So today, if you look at it, right, you have HBM or co-packaged memory, then you go to DDR, then you go to a burst buffer or a nearby flash device, then you go to a parallel file system, and then your 5th tier is going to be your campaign storage. Campaign storage. That can be object-based, like cheap spindles, maybe some people call tape. It's basically long-term storage. So you have 5 tiers that you need to pay up from the CapEx, and you need to pay the energy for it. It's killing you. Eventually, I think we need to get to a place where 2 of those get shot. One is DDR. So you're basically going to move straight from HBM over to some kind of NVM. And that NVM may be flash or something next, right? There's a lot of new technologies in NVM that are coming up. And then we need to shoot luster. So that's a provocative statement. And then once you stop spending so much money on luster, you can actually put it on Ceph or pick your favorite object here that's much cheaper. And then you have data movers that move in the data on your NVM that's much closer to your node, where you get much better aggregate bandwidth. But that means, and I'm going back to the users, that means that we probably need to ditch strict POSIX compliance. Because you might have a distributed namespace, you might have something else that you're not fully used to like you have today.
I like that answer because it was provocative and specific. Andrew, how's ECP looking at this problem? I'm about 5 minutes away from taking my first audience question because I want to do that too.
Well, I mean, there's a certain sense that we have bigger problems, but also there's a movement, and it's one that started and then stopped a few times, but now is picking up steam because there's going to be so much data created if we do simulations at this scale that we kind of won't even know what to do with it. So there's a huge movement in data compression, okay? And it's always been a kind of complex topic in scientific computing because you don't want to throw out anything of scientific relevance, right? So it's not just lossless, it's also lossy data compression. So we have a few projects that are funding different ways for compression projects to work directly with applications to be able to try to understand, what can be sacrificed and what can't, and what impact that has on the science. And I mean, that's very related to the storage, just because we sort of feel like there's too much data created for discovery in some sense. We have to be able to reduce it to the portion that's most likely to tell us something interesting. And I feel like that finally has a lot of momentum. I've been hearing about it for 20 years or so, but people are much more engaged.
All right, I want to go to Scott for kind of a grand scale question, and then everyone can reply to it, and then we'll go to the audience. But you're hearing all of these comments about architectures and the vendors' approaches. What I'd like to get a sense of is, what do you think the profile of a system needs to look like before it becomes commercially adoptable or something that people are going to want to buy? If you consider the cost, the power, resiliency, manageability, programming model, architecture, all the stuff they're throwing out, what does this need to start looking like before it leaves the realm of being a national lab project and being something that, all right, I can write an RFP and I might buy one of these?
You almost answered the question by saying, comparing it to a national lab project. I think traditionally we followed the national labs fairly closely, from Linux clusters to GPU usages. And I think Keith has used the term draft behind the national labs for us to be able to get to exascale. So usability, clear demonstration of usability, and following what I'm assuming it's going to be following what the national labs do, and keep in close contact and see how soon it's ready for something that we can use.
What are the prime components of usability in that statement? Usability, you can put it on the chart, but people could take a lot of different perspectives on what that word means.
Yeah. I mean, I'm going to end up repeating my last slide, you know, fault tolerance, programmability, those are keys. I mean, but
resiliency, programmability, that's fair. You just put those right as your top two. Yeah. Thor, you've been involved in some of these exascale projects. You know, you're hearing feedback here. What do you think is that lag between it's a national lab project and these are things that we're selling? And do you agree with the assessment of what those need to look like?
Well, certainly it's hard to disagree with what Scott said are the needs.
I try not to disagree with Scott.
I think as we view the challenges that the enterprise is facing, right, and and what it may require to get to that levels of computing, that obviously has to connect directly to codes that are available, performant, and obviously revenue that's on the other side of that, right? And so I think it's a matter of, I guess it goes back to the application, right? And are the applications going to be there that can deliver business value? And again, across things like simulation and modeling and AI and so forth.
I, in particular, do want to get Nick's view on that, but I want to get an audience question first, then I'm going to come back to some of these other ones. Here.
Great presentations, but I have to ask, just because it's always in the media and this group is going to know whatever the current state of conversation is, but I haven't heard quantum computing brought up at all.
Anyone want to take a swing at quantum computing?
For oil and gas?
Sorry, what was your answer?
For oil and gas?
For oil and gas. Well, for anything.
I don't think I can parse that way. Quantum computing for oil and gas, that's just, I don't know.
In a sense, I'm glad it came up. Anyone remember the HPCS project that poured a lot of money into different vendor architectures going back to 15 years ago? And the reason I mention it is because that project through DARPA specifically said these are the architectures that will bridge us from now to the future promise of quantum computing. That's what it said right in there. Now, I think quantum's still a little farther down the path than where it was envisioned to be 15 years ago. That said, we're starting to see some very real projects around quantum, and I think the first applications are going to be in areas like material sciences. It was explained to me once very well by a representative in the IBM quantum computing group, where he said you're looking for things that have very few inputs and then a large potential solution space and one optimal output. And there are a few sciences areas that go there. It's hard to compare to the whole exa talk because you're talking about something that's 50 qubits as opposed to one exaflop, and it's just difficult to say what's where. I think by the time these exascale systems come out, we're not looking at anything close to quantum supremacy, although we might have one or two viable quantum commercial applications. Well, probably more than two, but I'm not worried about the HPC industry disappearing into quantum in the next 5 to 10 years.
I think it would be a subset, like
a quantum accelerator within an HPC application. It's a nice idea. It's theoretically possible. Does anyone on the panel also want to go after that? No? No. Go over there.
Yes, I don't understand qubits either, but I wonder if anyone can answer what would be the unit rate, sort of cost per day of this system, an exabyte system. Because I think, for me, I would like to work on a problem that can afford that bill, and I think as a comment that the oil and gas industry is maybe the place for it, because it's one of the few places I know where we're doing $20, $30 billion projects. But that involves the platform, the plant, the wells, definitely not seismic, because seismic is today, you know, I say we cannot afford to drive that curve any further, but it has to then integrate, and I think it challenged this thing of doing new things with the system. But what will it cost me to run on that system one day?
So let me see if I can recap your question. The question is, what is the effective cost per day of an Exascale system? Do you intend to include hardware, software, staff, facilities, services,
Everything.
the whole
I mean,
thing?
I run on an
Full
XC40
budget,
system
all
today,
in.
and they charge me per day, you know.
Cost per day to own and operate and manage an Exascale system.
So the energy is easy. We can start with that, right? So if it's 40 megawatts and it's $1 million a megawatt a year, you're looking at roughly 100K a day for energy alone. Then add people and all of that.
I'm thinking it's $1 million a day. Hardware, software. It's going to be one hell of a problem to solve. If they can afford that.
Anyone else have an answer there?
I think we won't be able to afford it until it fits our current budgets. I mean, our budgets aren't that elastic.
So
Well,
here's,
this is a good point, right, is the cost curves come down on these things. Exascale on day one is a lot more expensive than Exascale 5 years in.
But, you know,
And it wouldn't surprise me if we lag National Labs by that. Sorry.
well, but that's a good point, but, so I'm going to do something provocative. If you were to ask Thor, if he built a processor specifically for Exascale, is that a money-making venture? And his answer would be no. He has to build something that he can get into mainstream product in order for the company to make money. Otherwise, they won't do it. And that's how Exascale will be cheaper, is when you can get it into more, you can get those technologies into more commodity hardware and drive it to scale.
let me answer a slightly different version of the question. One of the things you need to do to get to an Exascale system is to build a petaflop in a rack. Actually, you'd like to get about 5 petaflops in a rack. And the big question that people are debating is, for many of these industries, does it make more sense to get 200 5 petaflop systems out there or one single exaflop system? And I think the answer is going to be, in many cases, a lot of cheap 5 petaflop one rack systems spread around the country.
If it's that much cheaper per flop, yeah, I think that's true.
Mm-hmm.
Yeah.
But the Exascale program is going to drive that to happen.
But this is a conversation we had back at the Petascale era. Would you rather have one Petascale system or 1,000 Terascale systems? And the truth is, you go have both, right? At the leading edge, people push into petaflops, and in the meanwhile, the bulk of the HPC market starts investing in Terascale, which we didn't call those Petascale and Terascale at the time. We called them petaflops and exaflops. Scale was something we invented for Exa to have a nice arbitrary non-meaning to it. We take a mathematical prefix like Exa that has a specific meaning to it and put it in front of scale. It's like, you know, wow, that problem must be petahard. I mean, it has a specific prefix with a meaningless base, so it's kind of an interesting word to me. There was a question right in the front here.
This is a general observation from the presentations I've seen. One of the presentations Thor has presented is he mentioned data that is being generated by individual users. For example, something like 1.5 terabyte per day or month. Now, that data is being generated, and we are expecting many more industries with IoTs to generate data. For the current day, the success of the hyperscale service providers, they have been able to use that data and put an ARPU, or per user, what is the value for them, whether it be Facebook or Google. They have been able to quantify that per user is like $5 or $6, whatever is the number, I don't know, but at least that's been the quantification. So since this being oil and gas industry experts here, I was just wondering and curious if in order the computation that you do for HPC is from your perspective, from the industry perspective, it's an expense. It's a cost of finding the resources. So what kind of value do you put on the data? For example, in order to find a well that is producing X barrels or something, then in terms of revenue, how much do you need to spend compute resources? What kind of data do you generate, right? Is there any kind of studies or benchmarks?
The question is basically about economic justification of a new supercomputer infrastructure as you're going for a new level of capability. What metrics do you see out there? This is something that we pursued in our research of the United States Council on Competitiveness. There's a report you can download for free from the council website called Solve, the Exascale effect. You can Google for that or email me and I'll send you a link to it. We found a lot of different metrics for that, but I'm interested in I was also stalling for time as the panel got to think of their answers to it. Where do you see in terms of economic justifications for investing in these new architectures? They don't see any. There's no economic justification.
God, yeah.
Right, metric could be anything. It doesn't have to be strict ROI. It could be justification based on some new project, or I can process this many petabytes of data and need to do that for my next initiative.
So I'll say generally that an ECP, this is the starting point, like I said in my talk. So in order to bid for an ECP applications project, you have to say exactly what it is that you can't do now, that if you could harness the performance of an exascale machine, you could do, that is impactful, whether it's for national security, whether it's for energy. And so, of course, the return on investment isn't as obvious, but if you don't have that as a starting point, then the whole thing is pointless. It's just sort of an exercise in, I guess, trying to push the hardware forward. So, you know, every one of the projects has, they're not going to all succeed, right? But every one of them knows what their target is. And if you sort of flip around the previous discussion, instead of being, you know, pessimistic about how difficult and expensive it is, just say, if you could run something 50 times bigger or faster, or with, you know, some way of defining 50 times, you know, what would the impact be on your industry or on your research project? And, you know, use that to decide whether it's worth buying it and paying the power bill or not.
That's exactly how we had to pursue it when we ran a survey on this for the council, that the most people could kind of conceive of was the idea of 100 times more than they're doing right now, which meant unless they were already running at 10 petaflops, it's hard for them to get a concept of what exaflops will mean to them. But there was a lot of faith in the trickle down here to that level. Nick, you were about to dive in there.
So I think that's the important part. And it goes back to the previous question of 1 exascale versus 110 petaflops or whatever. And that's how we see it as a vendor, and I think it's true for all the other vendors as well. The exascale machine is kind of that uber achievement, and there are a lot of things that we need to do both on the compute, on the memory subsystem, on the interconnect, that needs to be done technologically to achieve that, right? I can use the optics I talked about. We need to drive those optics at that cost point, at that energy level, in order to actually make a capable exascale system happen. But once we drive that, and it's true for all the other sub-technologies, then these technologies become available to commercial HPC, to the oil and gas. And that's the key message I'd like people to take away from that. The same way the applications need to have a grand challenge and have a ripple through, it's true as well, and that I think that's most fundamental. The reason why we're funding all of those technologies, yes, we'd like to make the DOE happy, but we know that's because we're going to be able to sell 1/100th or 1/10th of an exascale to all of our customers with those technologies. And then the question you then ask them is, okay, you're going to get like a 10 petaflop or 100 petaflop system. What if you could get a fabric that would have 10x the bandwidth of what you got today for the same price? And just giving them one order of magnitude on memory bandwidth, on fabric bandwidth, or on compute, and then people start thinking, and they go like, oh yeah, this is really a big issue for me, and I'm going to jump on that.
Or
Go ahead, Steve.
How can you get your answer at least, 10x faster or something like that? Which, you may be able to do, well, you could have 2 petaflop machines or 2 exaflop machines, one would not be able to get you that answer and the other could, because they just have different architectural concepts. And so if I may, Andrew, one more. I think the thing that Andrew hit on that is the one I think is the most important aspect of Exascale is hardware-software co-design, where the applications guys and the hardware guys are sitting down before the hardware is actually defined, and they're telling the hardware people, this is what's happening, and the hardware guys are saying, this is what we can do and can't do. You know, these are going to be kind of the trade-offs, and they make those trade-offs. I mean, we're doing it on the memory side, Intel's doing it on the processor side. We're going to gain so much from that to build more efficient systems.
That's actually very interesting, because I've been sort of seeing this shift to Exascale as a continuous transition. You're describing it as a step function change.
There's going to be some significant change, and this is where oil and gas can form a hardware-software co-design capability like the national labs. Instead of drafting on them, you may have requirements that may be different than theirs.
Excellent. Thank you. Good point.
And you drive higher margin profiles than them. So
Well, that's true too.
Addison?
As we've started relating to some of the more volume part of the HPC market, I want to come back to one of the topics we hit right as we were 1 minute in, which is relating to the hyperscale market. If we look at the relationship between HPC and supercomputing and hyperscale, the largest supercomputer installations in the world are usually on the order of $100 million. In 2016, we counted 8 companies that spent over $1 billion a year on IT on the hyperscale side in the top tier. In 2017, I'm already convinced that number's at least 10 and likely 11 or 12. We've got to do a little more fine counting on the market methodology. Companies spending over $1 billion in the top tier of hyperscale. So the question is, you know, as it relates to our industry, what effect does that hyperscale market have on the HPC path to exascale as we look at architecture, standards, software, skilled people? How is our industry being skewed because of hyperscale? I also sent you this question last week.
Well, it's being skewed in a big way because they're getting the bulk of our attention.
They're getting the bulk of your attention at Micron specifically.
They're getting the bulk of my attention at Micron specifically, and when I
Intel's never heard of them, by the way. They don't.
Actually, when I was at Intel, they got the bulk of our attention as well.
Yep.
Okay, you know, instructions like pop count. AMD and Intel put pop count. It's you know, counting the population for put that instruction specifically in there because there was a need from the hyperscalers. They saw a value in that for search. The request came from somewhere else, but it was the hyperscalers that said, yes, we want to see that kind of thing.
Does that mean it's proportionally harder to get interest in HPC or exascale because the big money is in the hyperscale side?
No, so that's a great question, and thank you for doing that.
Well,
it was really more, it was a filter. So requests would come in, and the first thing we would look at is, okay, where's the economic value in the broader market? Now, in a lot of cases, if they said, yeah, we could use it or not use it, that's fine. But if it was, no, we'll never use something like that, then we'd really have to wait. Because like on a microprocessor, every time you add an instruction and you break into the decoders, that's the most sensitive part of that machine, and it takes, you know, tons of validation and verification to make sure you haven't broken anything.
Thor, you got nervous when I said your name before, so I'm going to call on you specifically because of that. How are you evaluating this hyperscale versus exascale trade-off?
Well, I think there's certainly commonalities that play well towards establishing the right hardware solutions and
you talked about a convergence of data and HPC. Is that where you're going with your answer? Really, the hyperscale and the exascale need the same thing?
Well, yeah. I mean, certainly there's that, and as we think about AI as a service or deep learning as a service, you know, the ways of providing these capabilities, or HPC as a service, right? Or ways of providing these capabilities in a remote, maybe off-premises way. That there's a path towards supporting HPC, if you will, through that model. And if hyperscale is the efficiencies are there, then that's a deployment or fulfillment path. And certainly, there's always going to be a need for on-prem computing and the efficiencies that may come from an enterprise having that capability.
But here's my concern with that is, does that lead to a line of thinking where computing is just a fungible commodity and it doesn't matter what form it takes? You just buy computing by the pound.
Well, I mean, one of the questions, that was asked about how much does Exascale cost? I mean, sometimes it's how much does computing cost based on who's providing it, right? And if it's as a service, it's what that service provider wants to charge for it. But I think as we look at the move to Exascale, it's there are efficiencies going to be found in different places, but fundamentally, what is that enterprise going to what drives the best ROI for that enterprise? And if it's HPC, national lab resource, or a hyperscale provider, then that's where it could go. But there's always going to be individual considerations across all these different deployment options.
We're stirring people up, and if
Yeah,
I don't
we
get
have
more
a-
questions from the
yeah,
audience, there's
we have
going to be a
question back
revolt.
here.
Thank you. My question is HPC, like the term, like high performance computing, is it losing its utility in terms of how useful it is as a term? And I think the last panel question was talking about hyperscale. And I think if we think about Segal's answer for what were going to be the first applications we see on the Exascale, things that were listed were things that look like ensembles, things that look like training. If we talk about FWI, all of these things are massively parallel. Sort of like map, reduce, type computation. What it isn't, what it doesn't require is low latency point-to-point across the entire machine. So if one's objective then from a business perspective was to solve problems that look like FWI, RTM, any machine learning, like all of these types of problems, then there's actually a pretty stupid investment of money to pay the premium for low latency point to point. Instead, you should be, well, this goes back as well to the other answer, the understanding the difference between capability and capacity compute. Instead, a much sensible expenditure would be to buy 1,000 Petascale machines. So I guess remind people.
What's your question?
Remind people of my question. Is HPC talking about HPC and Exascale? Is that still a useful term?
Is
Or do we
HPC
need
still
to
a
talk about
useful
something
I
different?
think it's useful for precisely the reason you just said, is because it makes a distinction between those two things. I mean, so of course, physics simulation is not going to be reduced to quasi-independent computing elements that don't need low latency communication. I mean, that's not going away. That hasn't changed at all. So in ensembles, frankly, you wouldn't justify an Exascale machine if you were doing independent ensembles, right? So I think what you think of as traditional simulation, that everything is about being able to communicate at very low latency across every node in the system, because you're doing tightly integrated, physics computations, you're converging solvers and so forth. That hasn't changed at all, from my view. I mean, there could be other uses that you call hyperscale, where independently you can just scale up the computing resources, but I think it's important to have a different term for that, because it sounds like a very different thing to me.
Sorry.
Go ahead and finish.
So I think it's very interesting that Andrew gave the hardware guy answer, because I think the most important difference is the runtime environment, right? On a hyperscale, the runtime environment, I mean, you're going to get 10,000 single OS instances, and you can scale it out as any way you want. But a true HPC system, you're going to have an MPI runtime, or you're going to have an HPE runtime. And then you're going to run one job that's going to have to scale across 10,000 nodes. And when one fails, you need to restart from the checkpoint or recover. And that's what makes HPC very different from hyperscalers.
We have one more from the geo industry here question.
I'll give you the analyst view to that question, which is, I would interpret it as, is there a segment of enterprise computing that gets driven predominantly by performance characteristics in purchasing that's distinct from general IT investment? That's the market we track. Yes, now we have to call it something. HPC is as good a term as we have. We've revisited that term about 3 times a year my entire career in the industry and haven't come up with anything better. If you think of something, let me know. Next question.
Okay, I have a geophysical question, so it's probably for Scott. I heard that number of $1 million a day to support the computing operation here. And I just think about how much better images do we need in order to make intelligent drilling decisions, and how much more detail and elaboration do we need in the seismic acquisition to support this major computing effort?
Boy, I wish I knew the answers to those.
Hey, or put another way, people used to drill for oil before they had computers, so what do you need this thing for?
To get a better answer than we used to, yeah. Deeper, higher resolution. I mean, there's not a simple answer. This kind of thing requires trying things, pushing the limits, and see what works. There's not an easy answer.
I look forward to a high bandwidth future. I've worked on a lot of high bandwidth systems, and I find because there's less cache, I have to scan through the data set more times. So if it's twice the bandwidth, I have to scan through the data set twice, losing all the advantage. So I guess in combination with that, we'll need some cache or something like that. But I didn't hear anything about that. Is there any comment?
Well, you will, but I think the caches will be different.
Microphone on?
No, it's not.
So to answer your question again, yeah, caches will be around for a while, but they won't necessarily be the small, short line processor caches. There can be memory and storage size caches, and even when you look at, even when we've looked at workloads like HPCG and graph analytics, if you do the cache and the line size correctly, the hit rates are actually very good. And those are considered sparse types operations. So I think you will start to see more, more in the memory and storage subsystem side in terms of buffering and caching. They'll be called caches, but they're not processor caches by any stretch of the imagination.
Yes, everyone is going to look at building bigger and better caches. But my understanding is a lot of the interesting workloads do not cache very well.
They don't cache very well in the processor caches. We have yet to find, like HPCG, we're getting hit rates at 85% in a 64 meg to 128 meg cache with the appropriate line size and associativity. And we built 6 models to try to prove that wrong, and we haven't broken it yet. We're working on number 7. So those are opportunities.
There's one final question here, and then you can wrap up.
So do you think that Exascale will find more usage in data analytics and data sciences areas more so than modeling and simulation areas?
So is Exascale more a data analytics application or more an HPC application? Thor, you think those are the same thing going forward?
Well, the ability for the data to feed the compute, right, to get the best and quickest return on your simulation and modeling, to then feed deep learning, right, so that you get the right inferences, the right conclusions from those outputs is the process. I'm not saying they're the same thing, but the convergence on the architecture certainly has value to customers.
Nick, do you have an opinion there? Analytics versus HPC for Exascale?
I think they should run in tandem. Like the whole, Doug talked about that, using AI to steer computation as it's going, using Viz as the computation is happening. So this is kind of emerging right now. It's not used generally, but I think the two kind of really grow together and kind of feed each other. I think Andrew is probably might have some of the best insight on that.
Andrew?
I think that's the idea. I agree. I think it's very nascent. I mean, people tend to get out ahead of what's really happening. So, I mean, there's a recent DOE report on the state of machine learning in the traditional simulation field. The relationship between them, you see a lot of very interesting ideas and a lot of hope, but there hasn't really been a lot done concretely. So, I think it's good speculation, but it's just that.
Scott? Just keep coming down the line here.
I don't really have anything to add beyond what they've said there.
All right, Steve?
Yeah, I agree with I actually agree with Andrew.
Easy to agree with Andrew. He's got the first Exascale machines. Mike?
The only thing I'll add is that
And I'm never wrong.
when you do data analytics, say like an overnight batch job, and there's not much benefit from increasing the speed of that by a factor of 2. It's when you cross the threshold where you can go from an overnight batch to do it in real time. You know, you reach a point where suddenly new things become possible. That's where the transition happens.
Cup of coffee time.
Yeah, cup of coffee time.
All right, I am interested in how these start to overlap, and in fact, we started probing this in our most recent HPC survey about the overlap between analytics and AI with the HPC space. And to me, you know, analytics is such a general term now. It's hard to imagine what kind of computing can't be rebranded as analytics. You know, everyone's doing analytics right now, but when we look forward to AI, I think there are a lot of HPC applications that we see out there in the market that could start integrating AI as part of it. Like, for how long have we talked about engineers in the loop in multi-physics problems? And it never really took off, but could you get an AI in the loop to start looking for optimizations in your designs, say for a manufacturer, to keep iterating the design towards some optimization? Or something as simple as object storage for trying to promote data to a hotter tier of storage before the request for that data comes, because you're looking at the pattern, right? You don't want to have that data be on the cold storage when you first ask for it. So I think there are a lot of, I mean, there are far-flung areas of AI that could start moving into HPC. I have to ask one more question because I run the best pool that there is. Do you have a pick for the March Madness bracket? Rice is not in there, I'm sorry to say. There are 2 teams from Houston in the pool, though. Texas Southern has no chance. But Houston could go back to its Phi Slamma Jamma days. Any picks for the March Madness bracket?
Nebraska for the women.
Oh, Nebraska on the women's side.
I've got nieces
All right,
there.
please join me in thanking my panel. It's been a great day.